So, very good afternoon to everyone present here. Am I audible to all of you?
Yes,
Yes,
sir.
yes,
Ah, thank you. So, I hope you all had a refreshing break and are ready for another engaging session as part of our faculty development program. So, on behalf of organizing committee of this faculty development program, I again extend a warm welcome to all the participants and our distinguished guest speaker of this particular session. So it is my privilege to introduce our esteemed speaker, Dr. Subhopal, who is joining us online from IIT BHU. Dr. Subhopal, he is assistant professor in Department of Electrical Engineering in IIT BHU. Dr. Subho received the ME degree in electrical engineering from Jadavpur University, Kolkata in 2016 and the PhD degree in electrical engineering with power systems specialization from the Department of Electrical Engineering, IIT Roorkee in 2021. Before joining the IIT BHU, he worked as a postdoctoral research associate with the Indo-US UI Assist project at IIT Roorkee from 2021 to 2022, and as a result, sorry, and as a postdoctoral research associate at Washington State University, USA from 2022 to 2023. He has published more than 50 peer-reviewed research articles on the topics of power system optimization, distribution network, optimal power flow and energy management, power system resiliency, and the application of artificial intelligence techniques in power systems. Dr. Paul was recipient of the University Gold Medal for the standing first in order of merit in the ME degree from Jadavpur University in 2016. He was awarded with the Grid India Power System Award 2024 under the doctoral category of outstanding work by the Grid Controller of India Limited. He received the Prime Minister Early Career Research Grant PMECRG in 2015, awarded by the ANRF DST to carry out research on the electrical distribution networks. He was also the recipient of several Best Paper awards in different national and international IEEE conferences. Sir, we are truly honored to have you with us today to share the knowledge and experience. So now I would like to request Dr. Subho to kindly address the participant and deliver his expert lecture. I now hand over the session to Dr. Subhopal. Sir.
Thank you, Vishal sir, for giving me this opportunity and introducing me. So I will share my screen. Please allow for a minute. So is my screen visible?
Yeah, yes.
Okay. So I'll be talking about the resilience enhancement in power distribution grid. Specifically, I will talk about distribution networks against the extreme weather events, which is mainly the cyclones happening at the Bay of Bengal areas, how to like mitigate and which kind of resiliency measures we can take as a power engineers. So as we all know that that climate change is not I could say the futuristic thing now as of now. Now it has become a harsh reality, and this is causing severe cyclones in Indian Ocean area, typhoons in Pacific Oceans, and hurricanes in the Atlantic Ocean. And the bad news is that the frequency of this hazards or our extreme weather events has increased in past few decades. So if you can see from the back, like from 1970s to 1990s kind of thing, this has occurred mostly like uh, once or twice in a year. But currently it is happening almost 5 to 6 times in a year. Like even recently we also got a cyclone from Bay of Bengal area. So this is not only the concern of the Indian tropical region, but also the global problem. Even in the US, people are also aggressively doing research on that how to make the distribution grid more resilient against those events, because sometimes these events causes the power outages for a few days. So, and that is why I am discussing it today. And you can see, first we'll see that what are the extreme weather events we are talking about and why from Indian perspective this is very important. So, as we all know that India has a very big coastal area, almost 7,500 kilometers of coastal area we have, and mostly two seas and one ocean we are like having this coastal area. And the Bay of Bengal area is mostly the vulnerable position for this extreme weather events. And if you can see that the states which are majorly affected by this extreme cyclones, that is one is here obviously the West Bengal, Odisha, and Andhra and Tamil Nadu. Those are at the east coast area. And the west coast areas like the Gujarat, Maharashtra, Karnataka, and the Kerala, they are also having moderate chance of like being attacked by cyclones. But if you see the tendency for the last 50 years, that is from 1970 to 2020, that almost 117 cyclones we got in this 50 years. But for in within this last 10 years only, that is from 2010 or 11 to 2020, we got almost 33 cyclones. So that is the major share because of this global warming and the climate change effect. So this enhances the rising annual frequency that we are getting almost 4 to 5 cyclones. And if you see the mid image that we can see that this green lines which are the depression region, depression of the climatic region, that means these are the normal your uh, monsoon air which comes from the Bay of Bengal area. But if you see the blue and the red, those are actually the cyclone trajectories or cyclone events happened in last 1 decade. So you can see the number of red and the blue trajectories, those are increasing heavily. And the red one, that is the super cyclone storm, this has like a major share within this events. So if we see the what are the few major events we have experienced in Bay of Bengal, obviously the Fani and then Amphan, Asani and Dana all are at the Bay of Bengal area. But if you can see, they have a trajectory or the track. It is not like that it has just did a landfall at Odisha coastal area or West Bengal coastal area and it died out. It will enter from the sea into the land and then it will again progressed through the land area. So that actually causes the destruction in the power system. And that progressiveness of the cyclones that majorly calls for the fallen of the electricity poles. As you can see in the images, what is caused by the Fani in 2019, that and to cope up from this situation is very difficult for any power grid because you know this all the infrastructure is damaged. Okay, so mostly the distribution poles, distribution lines, outdoor small substations, your small pole mounted transformers, they are mainly the most vulnerable equipment which are more exposed to this extreme weather events. So if we see the statistics that how much that is affecting. So if you see that the funny, which is in 2019, almost that has paralyzed the power grid by blacking a blackout region of almost 3.5 million people in Bhubaneswar and Puri, and they got their supply back after 3 to 10 days. So they have to live in dark for almost 10 days time. And the similar things happen for Cyclone Amphan and Cyclone Iyas as well. So if some extra hazard or a cyclone attacks to a coastal distribution grid, so that area or that portion, those customers has to live in dark for almost 1 to 2 weeks time. So that seriously questions the reliability to the power grid or to the local distribution utility. And that reduces also the trustworthiness of those utilities in front of their customers. So if you see, those are the destruction phases, like when the super cyclones attack the distribution network. But in general, whenever, let's say, a cyclone or a very high wind flows through the region, what are the normal challenges the power system faces? First one, obviously, that is the transmission or the distribution infrastructure impact, that will the cyclone will cause the fault in the distribution lines, leading to some disturbances, and that will cause the reduction, or you can say the shutdown of the loads which has been affected. So you can see there is a huge reduction in the demand suddenly, and that sharp drop cannot be easily be mitigated by the generators. Like the generators cannot cope up with this drop by reducing it inertia. So we have to, it will take some time because of this mechanical time constant to reduce that generation, and that will cause within that time period you can see the increase in the frequency, because your inertia is very high but your load is very low, your generation is very high, so you will have a higher in frequency and as well as the over voltage problem. So you can see in the right hand side image where this has been taken from the POSOCO or the Grid India report, which is noted for the western region, western grid of our power system in India, which has been affected by this Oki cyclone. And you can see that suddenly at the daytime, when the cyclone actually attacked or passes through the region, suddenly you can see there is a drop of almost 8 gigawatt. But obviously your generators are generating those 8 gigawatt, and that will cause a sharp increase in the frequency. So this yellow graph is your frequency. So you can see a sharp increase in the frequency, and major western area region which has not been affected by that cyclone, you can see the red spots which are notifying that those buses in the network has experienced over voltage condition, and that over voltage is very high, that is not in the permissible limit of our power grid. So obviously then at that time the voltage control actions we have to take, we have to turn on few reactive power absorbers like the your inductors to absorb more power, reactive powers, or we have to turn on few dump loads to also do the load balancing, load and generation balancing. But those things are a costly solution because you are just generating from the thermal power plant and you are wasting that energy to a dump load. Apart from that, each and every cyclone obviously causes an economic damage also to the power grid. So this is just statistics of the Odisha, which is the most prone, or you can say the most affected state of our country because of this cyclone or the extreme weather events. So you can see only the electricity damage, that means the power grid damage is almost costing sometime it is touching even the 8,000 crore. So there's a very huge amount of investment we are losing because of this extreme weather events. So there comes the study, which is we call it as a resiliency study. So these are the background, and you can see we have not even we have this economic loss, we have technical loss, and also the service utilities. They are also facing the reliability issues in front of their customers. So to cope up with this or to manage these scenarios, generally this resiliency study has come into the market for last few years in the power system study. The resiliency is actually means when you can cope up from your disturbance and can bounce back from the disturbance to your normal operating scenario. That means you were operating previously to your normal operating conditions. You got that disturbance, so some changes obviously will happen. You cannot run at the normal uh, your normal condition. You will do some modifications, but that will be minimal effect. That will affect your system or your customers in a very minimal manner. And then again, when the disturbance will pass over, that means when the cyclone will go from your region, at that time your power system can again cope up from those disturbances and can again at least reach very closer to your normal operating condition. If that is the case, if that is possible for any power grid or any distribution grid, then we can call it as a resilient grid. So that's why this resilience now broadly refers to the system ability to rebound from the severe disruptions. And previously it has been used for ecological systems, but uh, from 2000 onwards, we are adopting this analysis, or you can say the studies in the power system as well. So why we are more concerned about the distribution network? Because transmission resiliency has already been explored in a very huge manner for when it started, when it started in power system. But the distribution networks are mostly, you can say, neglected. People are, we are solving optimal power flow, we are solving reliability analysis and all these things for distribution network. But this resiliency study for distribution network has been started in very recent time. So, but that is very highly needed because the distribution network is the first network where the customers are connected. So you make your power system or the transmission grid very strong, but until unless your distribution grids are strong, if they remain keeps as a vulnerable situation, then and they got destroyed because of your uh, this extreme weather events, then you are you can do whatever with your transmission grid, still you cannot cater your customers. So this, and mostly the distribution grids like your poles, your lines, those are not very strong because normally we use very one single pole. You have noticed the distribution poles, very thin concrete or wood or steel poles are used. Those are very brittle in front of a very high wind. So, and those are also very much exposed to this uh, uh, extreme weather events. And as the poles and lines are not at very high level, that means from the ground, so it is a very high tendency whenever high wind will blow at your region, a branch of a tree can easily fall down on that line and can create a fault, or it can disrupt your service. And again, this with this condition, if you see that, if you apart from that problems, like where the problems is there, obviously the solution is also there. So the distribution grid is vulnerable, but also distribution grid has the distributed energy resources because we are keeps on increasing the solar panels, batteries, and electric vehicles. So those can act as a local sources. If something happens to the main grid and the customer cannot be catered from the main grid, then at least those distributed energy resources present at the local area or at the customer end can supply few portion of the load. So means it is like staying in dark, it is better to staying just a few bulbs are on at your home. So at least the reliability of the system will increase. So the distribution grid has that provision, or you can say they can leverage that benefit, that it has this local solutions in hand. And obviously, the government is very aggressive that it is going towards the 24/7 power supply to the customers, whatever is the situation. So that also in lining with that economic and the regulatory policy, the distribution network utilities are also like they are doing this resiliency studies nowadays. So the distribution network resiliency is mainly refers to the ability of an electrical power distribution system to withstand, obviously, adapt and recover rapidly from the high impact but low probability events, because this extreme weather events are not very frequently happens in a like year. That means it's a 4 to 5 times or 6 times or 7 times. It will not happen like 100 times in an year. So this is a very low probability event, but when it happens, it just destroys your entire system. So to cope up with that, when we call a distribution network resilient, what we actually want from a system, we want that the system must be robust. That means it has a physical strength that it can withstand against those natural hazards. Second, it has a redundancy. That means if one area is affected and the power path of that area has been affected and you cannot cater to those customers, you will always have a alternative path, alternative solution to cater those customers. Maybe those are longer paths, but at least you have some alternative paths. So if you have a redundancy, then your system can even operate even after some disturbances. Then you have resourcefulness. That means those some mobile resources like your electric vehicles, or maybe you have some static resources, that is your battery energy storage, or any fuel cell, or any kind of local DGs, diesel generators, which can supply your load from the local area. And then your rapidity, that means how fast you can recover from the disturbance or from disturbing states and can come to your original or the normal operating condition. So depending upon that, we normally take two different kind of resiliency analysis. One is called the short-term resiliency analysis, and the second one is called the long-term resiliency analysis. Now, what is the difference between both of them, the short-term resiliency and the long-term resiliency? The short-term resiliency analysis, or the, you can say, the this uh, measures we adapt when we have not predicted something. That means we know this disturbance will come, but we are not prepared with for it. So the disturbance came, destroyed your distribution network, and it passes by. So after that, what you have to do? So that will just you can say the corrective measures you will adapt after the disturbance has happened or after the extreme weather events has happened to ensure the continuity to the supply. Maybe by mobile, like by turning on your local energy resources or turning on your local diesel generators, and that will be done to ensure some of the continuity to some of the local critical loads. That means the hospitals, or the, you can say, the health centers, or or government offices, which needs to be run even at the your disaster events. Then you have the this DERs and the policies that we have, that normally is changed at the time of short-term operational resiliency analysis. And after that, when you take all these corrective measures, they calculate the metrics. Those are the reliability metrics, which is like outage duration, or the your how many times you are affected by this outage. Those things are calculated, and those are like your satisfactory measures. If those are at the satisfactory level, you can say, okay, your short-term resiliency has been restored. So those are done by your smart operational controls for your local DERs, and doing a load balancing strategy just by cut down few loads like your flexible loads and scattering only the critical loads from your backup supplies. So those are the corrective measures. Now the second thing comes, which is called the predictive measures or preventative measures, where you will prepare your system at a long back, that if the disturbance will also come in their system, or the or a cyclone will attack your distribution grid, but your distribution grid is strong enough that it can withstand that disturbance and can continue the supply. So that is done by, let's say, you can physically strengthen your distribution poles or distribution lines. That can be done by checking the historical data, that obviously when a event happens, we maintain a logbook to enter all the like all the equipment we have lost. So you just study all those disaster data, and then from there you learn that which are your vulnerable points, or which are your vulnerable equipment in your system that needs to be strengthened at the planning time, when you are planning your power system, let's say 5 years or 10 years time. Then you will upgrade your infrastructure depending upon that. That means you will place a diesel generator to a location which is very prone to your cyclone, and you will then there only you will do the pole strengthening, or let's say line strengthening. Because this long term infrastructure resiliency works, these are the costly solutions, because you need to upgrade your entire system considering those events which are not very likely in the area in an year. That means for, let's say, for a 5 days or 10 days event, for an year time, year complete time, that you are investing thousands of crores. So you have to be very careful while adopting this long-term infrastructure resiliency, and you have to identify precisely those area in your network which are more vulnerable or more prone to the disturbance, and those areas is only needs to be strengthened by adopting your this grid hardening or any kind of infrastructure upgrade measures. So you will take this grid hardening methodologies, or you can do the distribution level stationary and mobile DERs. You can plan for your distribution network. So majorly, the short-term resiliency is an operational resiliency, and your long-term resiliency is like a planning resiliency. Then if we see that now how to measure this resiliency, because we are talking about that we want to make our system resilient, but when we will say that my system is resilient, so for that, generally in resiliency research, performance function, which is a trapezoid performance function, is mostly used, where it is says that first you will have the normal operation, obviously that is at the 100% level. Then you will get the alert of that system that something is coming, like some bad thing is going to happen with your system. That alert is coming, and obviously at that time the performance level of that system will drastically reduce, and that is the damage propagation state. And when the damage is done, your system will remain at that damaged state, because it to recover from that state it will take some time. So that is the post disturbance state, and after some time you will start recovering from there. And this recovering is mostly done in few stages. It is not like an one shot recovery. Obviously you will first do like turn on your local DGs to supply your critical loads. Then you will it will take some time to connect the customers one by one, and then you will again re-establish the entire facility which has been destructed, and then you will can say that okay, the recovery portion is completed. So it is just not an one shot thing. It will be a step by step process, and then after doing this entire process, where you will lie, that will say you that whether your system is resilient or not. So if you can go back again to at your 100% level of function performance level, then your system, you can say those are 100% resilient system. But normally that is very hard to achieve. So generally, obviously there is a gap between this like your normal operating condition and post recovery condition, and that will give you the resiliency index. So generally this resiliency index is measured for a system to define or to say how much resilient your system is. So if it is 1, if it is close to 1, that means you are able to achieve your performance level at the 100%. So that is the highest level. That is, and that is desirable as well. But in reality, that is not 1. But if it is coming out to be 0, that means you are remaining at the post disturbance. That is also not good. So the generally the we try as a power system engineer always to keep this resiliency index closer to 1. It is zero point 0.9 or 0.85 or 0.95, closer to 1. Making it 1 is very difficult, because making it 1 will take a huge amount of investment, and that will also take some time. Like after, let's say, when an event happened, after that, let's say 1 week time, this resiliency index can go to zero point 0.2 or zero point 0.3. That means only 30% work or performance you have recovered from those disasters after that disaster. Then slowly you build up your infrastructure. That will take years, obviously. So maybe after 2 to 3 years again you will achieve that 100% level. So this resiliency index is not a short-term index. It is actually a very long-term index. But as a power system operator, they always keeps on trying that how to maximize it. Now, how you will do this resiliency evaluation for a power system? First, obviously, you identify and classify those events, because, as I have mentioned, that when a high wind blows, it can be of three types. It is either a depression, that means just because of the temperature difference between the sea area and the land area, a high wind is coming from the sea area, which is the monsoon, obviously. So that is called a depression. Then the second level, which is called a cyclone, and then the third level, which is the super cyclone. So there are three different kinds of categories are there, and you have to understand for which kind of scenario you are trying to make your system resilient. Because if you are trying to make your system resilient against a depression, that makes no sense. Because your system is already very strong that it can withstand the normal monsoon. If it cannot, then your system is like very brittle one. So generally we focus on the cyclone and the super cyclone part. So depending upon that, we have to study the historical data, that which type of cyclones normally we encounter, what is the trajectory, where is the landfall, and how this actually traverse through the land, and at which places it is mostly affected. So those data of the cyclone is normally been captured, that is the magnitude, the likelihood in an area, that how much frequently these events are happening, the spatiotemporal distribution, and then we do this analysis at the both deterministic and the probabilistic level. Like, because one cyclone has taken one trajectory, it is not like it is 0% probability that the next cyclone will take the exactly the same trajectory, and even the speed of the cyclone. So obviously we have to go with the probabilistic model, that is mostly done by the statistical modeling of the cyclone. Then after considering the cyclone data, we after see what are the vulnerability analysis of the power system components. That means obviously when it will traverse through the land, it will traverse through a certain portion of the city or the rural areas. It is not like the entire city will become dark. It is possible, or the entire state will become dark. The some portion of the state or some portion of an area is like affected by that cyclone. So we have to identify those points, and we have to see what are the power system components are lying within that area. That can be a macro component, that is your power plant, your substation, poles, lines, or maybe the micro components, that is the circuit breakers or the switches. After gathering that data, you will see which equipment are more fragile to that wind speed. So we'll do that fragility curve analysis to model the probability of failure for each component. Because obviously which the component which are ground mounted, let's say a power transformer or a distribution transformer, which is a ground mounted distribution transformer, it has very low probability that will get experience failure when a high wind will blow. But the distribution lines or the poles, those are more exposed to those high wind. So there is a very high probability that they will fall down. So depending upon that, this probability scenarios has been identified. Then these components are assigned to various damage state, because the effect of the damages will not be same for each and every component when the cyclone will traverse. Some equipment may experience minor damage, some experience major damage, some experience total failure. So depending upon that, we have to identify which equipment is damaged and what is their damage level, and that will give you the weak links or fragile components in the network. Then we'll simulate, or you'll include those things in the power system. So obviously when this grid, some portions is de-energized or some portion is disconnected from your supply, so those portions needs to be cut out from your system. So if you cut out those system, then we have to do the analysis for rest of the energized portion. And we have to see whether my energized portion can sustain that disturbance or not. That means if we are experiencing any over voltage condition or over frequency condition, or let's say any cascading failure is happening or not. So all this thing analysis we have to do with the help of power system, normal power system, power flow analysis or optimal power flow analysis. And that will give you the response of the system or your power system to the disaster during the disaster time. And then comes the recovery and the restoration stage, where we'll see that how much disaster has been happened, how many human lives has been affected by this event, and how fast we can recover from that situation, and what are the corrective measures we will take. And that will give you that restoration time and level after disaster. So this is the broad overview of how to manage the generalized resiliency evaluation framework for a power system. Now, if you come to the specific way, that which are the stages we have to carry out in terms of mathematical analysis or in terms of you can say the software analysis. So there are majorly three stages we carry do. The first stage is obviously the data collection and generating the cyclone scenarios. Because cyclone will happen only because if you see the historical data, every year if you even have like three actual cyclones happening in your country, and you take even let's say the last 10 or 20 years data or 30 years data, you have only 100 data with you. So taking a decision from those 100 data is it is not a very practical solution. And second, what I have told, that occurring a cyclone or a extreme weather event exactly the same way what has been done, what has been experienced in past, that probability is also very low. So after collecting those historic hurricane or cyclone data, we have to generate some scenarios or some synthetic data out of it. So that is the first stage people carry out. Then the second stage comes where you will simulate this entire hurricane scenarios, whatever the actual scenarios and also the synthetic scenarios for to your distribution impact, to your distribution network or the power network. And we'll do this for each and every component present in the network. And we will see the vulnerability analysis. And as an outcome of that, we'll suggest a short term and long term measures. That is the corrective measures and the preventative measures. That is the system condition and the restoration measures for the short term and the grid hardening suggestion for the long term. So we'll start with the stage one, that is the data collection part. And it involves the total three kinds of operation or three kinds of data collection process. First one is obviously the hurricane data, hurricane track, and then wind field model. Because if a area is also affected, when a hurricane is traversing or going through an area, the neighboring areas also get affected because of the high wind and the rain. So that is called the wind field. That is the wind field of the entire hurricane. Or the hurricane main point or the eye, that is actually where the main effect will see. That is the nearby of that eye area will see the main effect. But apart from that, after the eye, like this radius of the cyclone, will see some storms or some high wind. So what is this wind field? So how much is that radius of that hurricane or the cyclone? And then what is their track, like in the land, how it will traverse through the land. That is the first data we have to collect, first type of data. Second type of data comes, that is the asset mapping. That means with that cyclone track, you map your power system assets which are falling under that track, and depending upon the geographic conditions. And then from there, we have to see the wind speed, because a cyclone which has the radius of, let's say, the same, their wind speed can be of different. So we have to check that wind speed interpolation as well. So specifically, if you see that which kind of hurricane or the cyclone data we collect for the resiliency analysis, that is the first is the meteorological data, that is the wind speed and the gust. We see the central pressure of the storm, we see the storm surge height, and we see the forward speed, that is the speed of the uh, cyclone to its forward direction, and the radius of the wind, that is the radius of the cyclone. Then we see the storm track, that is where actually the landfall is happening, like from the sea when it is entering to the land, what is the exact area, because that will be affected hugely, or that will experience the maximum disaster. So where is that exactly that point? Then we'll see the frequency, like how many times it is coming in an year, and also the historical intensity and the damage of the previous few years. Then we will see the geospatial data, that is the topography and the elevation, obviously, because if the hurricane enters to an hilly region, let's say if your your sea area or the coastal area also has some hills nearby, then your cyclone cannot traverse to a long distance. It will die out very fast. So what is the topology and the elevation, and what is the land cover? Obviously, if there are more trees and your lands are covers, because that's why we say that in Sundarban area, this mostly prevents that mangrove forest from the extreme weather events, or you can say the cyclones. So if those like vegetation is present in the geospatial in your land cover, then that will reduce the tendency or the effect of your cyclones. So those considerations are also taken as a data input data, and then your infrastructure data, that is your power system data. So considering all these scenarios or all this data, the hurricane wind field model is designed. So you can see the hurricane wind that it has an eye that is the center of the hurricane, and then till the uh, radius, if you move from the center to the radius, its wind speed keeps on increasing, and that has been represented by this curve that it is mostly increase exponentially. But when you will reach at the uh, this radius level, that is the maximum speed possible for the cyclone. And after that radius, if you cross that radius, after that your speed will start decreasing. So if RV max, that is if you're like the radius of your hurricane, so till RV max, your cyclone speed or the wind speed will keeps on increasing. And whenever you will cross that RV max or the maximum speed limit, after that your till the end of the cyclone area, the speed will start decreasing exponentially. And after that, after a certain distance, you will not even see any effect of the cyclone. So depending upon that, we have to check our power system component falls under which area of the cyclone. Is it closer to the cyclone eye? Then it will experience severe amount of intensity of this hazard. If it is from the RV max to the RS, then it will experience the hazard but not at that much maximum level. And then if it is beyond that RS, then it will not be affected or very minimally affected by the cyclone. So this wind field model tells you that if a power system component falls under your or your hurricane or the cyclone model, then will it be affected by that cyclone or it will not be affected by the cyclone. So to represent this, mostly a piecewise mathematical function is considered, which will take this model inside your power system analysis or the power system planning problem. Now, after considering that, you have your wind speed model, you have your tracks, everything with you. But as I have mentioned, that historical data for a certain hurricane is not enough to take a decision for the future. So those historical hurricane data, that is the track, speed, wind field, and the decay rate, those are stored, and from there we take we will generate the scenarios. And obviously, all hurricane data are not documented well, especially in our country. Mostly only the Fani, Amphan, and few others very critical super cyclone data are only been recorded properly. So only with 2 and 3 data you cannot like work properly. So what is normally done? You consider a specific cyclone or a specific hurricane and then perturb its few key parameters, which are the key dominating parameters of your cyclone. That is, first is the land location or the landfall location. It can be, it can hit to a particular region, but this can be 10 kilometers either side of that region, 10 to 20 kilometers either side of that region. So you perturb that initial location and generate 100 or 200 or 1000 scenarios. Then you see the translational speed of that hurricane. You see the angle, attack angle of that hurricane. You see the landfall decay rate, and also you see the radius of that hurricane. So take those cyclone data or the hurricane data, try to perturb all these parameters, all this key consideration by some amount, depending upon your level of uh, consideration. That means if you want to do a very worst case condition, you will take very huge amount of data perturbation. By taking the actual value as mean, normally we generate taking this as a normal distribution, generate a huge number of scenarios and take those scenarios for your further studies. And all this tracks or your speed, everything will give you a synthetic hurricane or a cyclone scenario. So then you generate those synthetic tracks using this climatic adaptation ETH Zurich. There is a tool they have developed. So this can easily, if you just fit this data like your uh, your speed data or wind data or landfall data, and then your track data like what is the length of the your cyclone this has been traversed, the distance. If you put all this data, then it will give you a synthetic track that you can see at the right hand side image, that this deep purple color, that is actually the cyclone happened at the Texas area. And then this dotted cyclone, the dotted synthetic events has been generated from that tool. So it will, you can see that you can generate enormous, like huge number of scenarios, but uh, you can see that it is varying. Like if actual attacking area is close to your Florida or close to your Texas area, but it is taking almost 10, 20 kilometers or 50 kilometers either way to create that track. So then you have 100 different scenarios or 200 different scenarios of your of your cyclone. Then you take those cyclone data and we'll do the further analysis with the power system. So the second stage, that is the impact of the cyclone on the distribution network component or the power system component. So the first work we'll do with this synthetic cyclone data, that is the fragility curve analysis. That means each and every component has a certain value of failure probability. Everyone is not equal. Even let's say a distribution pole, yet if it is an wooden pole, its fragility level or the failure or probability level will be lower or different compared if you made your pole with let's say concrete or steel. Similarly, if your distribution line, that is a single strand line, that is more brittle, or the failure probability will be very high compared to if you take a bundle conductor. So depending upon that, we have to study the fragility curve for each and every component. And from that fragility curve, because we'll see in the next slide, this fragility curve is highly dependent upon your situation or your analysis time, or what is the condition of that your hazards, or maybe and even the condition of that equipment itself. So depending upon that, when the actual your actual or the synthetic scenario of your hurricane you will mimic or you will implement on those equipment, we will see the damage probability. So that will give that whether your system is 90% probability of failure, or have 80% probability of failure, or 10% probability of failure. But obviously we are doing this analysis with a synthetic one, so we cannot be 100% sure with this probability level as well. So even to take consideration at the larger level, we do the scenario generation from that probability for that probability values as well. And that is done by your Monte Carlo simulation to generate, let's say, 1,000 number of probability scenarios for a single equipment to be failed. Now, how you can design this fragility curve for a particular equipment? First, we have to see the parameters. We have to define the parameters or the component what we want to do this study. Like it may be a pole, distribution pole, or it may be a distribution line, or it may be a substation, it may be a transformer, whatever, any kind of equipment. And we will collect its data, like its manufacturing time, its manufacturing year, maybe what is the age of that equipment, and where it is placed, whether it is exposed to the nature or not, or whether it is an inside like in home equipment. So depending upon that, this data has been collected. Then you will see the hazard type. That means which kind of extreme weather event or which kind of event we are going to experience. So this resiliency study we not only do for the cyclone, that is done for all kinds of natural hazards. We do it for the earthquake, we do it for the cyclone, we do it for the flood, any kind of natural events. So we have to see which kinds of hazards or the intense or the natural disaster we are considering, and depending upon that what is their intensity measures. That means your cyclone range from let's say 50 meter per second, the speed can range from 50 meters per second to let's say 70 meter per second. So the intensity measures can be start from 50 to 52, 53, and it can go up to 70. So the effect on that equipment at 50 meter per second is never be equal to the effect of if it is at the 70 meter per second. So we have to specify the intensity measures or the level of the intensity of that hazard. Then the third thing, which is that define the damage state. That means whether you want your system to be like for a particular intensity or particular hazard level, whether that will be minor affected. So if it is a minor affected, your fragility curve will be different. If it is a moderately affected, then it will be different. Or if it is complete failure, then it will be different. So depending upon that, you will segregate that whether you are studying for a minor damage or moderate damage or complete damage. And then you identify its electrical demand parameters or engineering demand parameters. That means let's say a pole is there. So you always want your pole to be 90 degrees standing tall from your ground. So if it is displaced or if it has been tilted by few angles from 90-degree, that means that is not a desirable condition. So that makes your pole more brittle or increase the probability of failure. So those are, we call it as a engineering demand parameters. So, or what is the level of sag you want for your line? So those are your engineering demand parameters, and depending upon that, we decide whether the system is minorly affected or extensive affected. That means when your pole has to be stand tall for 90 degree, exactly 90 degree, that means there is zero effect. Like even let's say your hazard has occurred, your wind has attacked that pole, but still at that time as well your pole is sustained or is able to stand tall at 90-degree. That means there is no effect of or there is zero effect on that pole. Let's say it tilted by 5 degrees, so we call it as a minor. Then it is tilted by let's say 15 degree, we call it moderate. Let's say it is 60 degree, then it is extensive, and it is completely fall on the ground, then we call it a complete disaster or complete failure. So those are the few parameters we have to define before proceeding to this fragility curve analysis. Then with this, all this data, we'll do this model generation. That means whether your system can sustain that or not. So there is two uh, methods normally been followed. One is the model based approach where you will do the finite element method. You have those as like your console software or any other kind of mechanical software. You design actually like a civil engineer people they normally do. They actually design those poles or the lines, those mechanical and check the mechanical strength of that equipment by varying the intensity level. So they vary the intensity level and see whether your equipment can sustain it or not. So that is the model based approach. But another approach that has been done, that is the statistical approach. That means you see the historical data for a particular equipment from other areas and see whether for a particular hazard level, whether that equipment has a tendency to fall down or not. If it has a tendency to fall down, that means it is a more hazard or more prone to failure. So depending upon that, you do the model. So that is the statistical or the empirical approach, and the first one is the model based approach. And after that, you set the damage threshold. That means how much damage if it happens to your network or your equipment, then you call it that now this is your equipment has been damaged and it is not capable now to cater your customers. That means let's say your pole has been displaced by 5 degree or 1 degree or 2 degree. That means it's a minor effect. So at that time we cannot disconnect the supply because still your pole can cater the customers. But if it has been tilted by 60 degree, that means it is very close to your ground. And at that time, if you still continue your power supply, that means that is a serious threat to the human lives. So where you will put that threshold, that how much hazard if you experience for a particular component, and after that you will say that now this component is not able to cater my customer, or is not in operation. So that threshold is specified, and from there, by different scenarios, this synthetic hurricane scenarios, you simulate those intensity measures for a particular equipment multiple times. You vary the intensity level you vary that scenarios, and you do this study repeatedly and note down the probability of its failure, because that means how many times the failure probability or the probability is exceeding your threshold level. You just note it down, and that will give you the failure probability. And that failure probability you plot or you fit for a particular probability distribution function. If you fit for a particular distribution, a probability distribution function, PDF, or cumulative distribution function, CDF, and if it is fits with, let's say, 90% or 95% accuracy, then we can say we got our fragility curve for a particular equipment. And we keep that for a fragility curve, we keep the x-axis at the level of the intensity, and at the y-axis we keep the probability of failure, or the failure probability, and that we save for the analysis of the resiliency analysis of the power system. So generally, whatever the power system equipments we have, they normally follow the log normal CDF, or cumulative distribution function, which you can see at the right hand side, that when the intensity measures, that is at the x-axis, it will keeps on increasing. The probability level, probability level of damage, that is the failure probability, will keeps on increasing. And after a certain time, when intensity measures will 1 minute. Okay, sorry. So when the intensity measure will exceed a particular value, so at that time your failure probability will become, let's say, 90% or 80%. Okay, so this is the plot for the fragility curve normally been followed for all the equipment, and the damage states are been decided. So this what I mentioned, that your fragility curve is designed for damage states. That means, let's say for a pole, the damage state is the first thing is the displacement. That is what I told, that whether your pole is been tilted or not, that is one damage. Second damage can be that because the lines are at the tip of that pole, and if that tip has broken, so you can say that your pole is not working. Still it is standing at the 90-degree, but the tip has broken, or an insulator of that tip has broken. So that means now you cannot operate with that pole. So there are different kind of damage states, and each damage state will give you different fragility curve. Okay, and also depending upon that, if you see the below image, that it will give you that depending upon the damage level, that whether it is a slight damage or minor damage, moderate damage, extensive damage, or the total damage, your probability, your fragility curve keeps on shifting. That means whether if you want a slight damage fragility curve, obviously at the low wind speed, your equipment will experience a slight damage, but it will not be completely damaged. So this slight damage fragility curve is at the extreme left. Then the moderate damage, if you increase the wind speed, then you will see that this moderate damage curve is there. Then you have that extensive, and then the total damage. So for experiencing a total damage or complete failure for a particular equipment, your wind speed or the intensity of your hazard has to be very high. So that will give you, let's say, 40% or 50% probability of complete failure of your system. But if you see this at that level, if you see whether my system will be minorly damaged or not, obviously that will happen. So that is an with 100% probability. So when your complete failure is 40% probability, your minor damage will be maybe at the 100%. Your moderate damage may be at the 98%, and your extensive damage is maybe at the 70% level. So you have to be very clear, or you have to be very specific for a particular intensity level of a of an hazard system or hazard event, which kind of failure statistics or which kind of failure scenarios you want to study. So depending upon that, you will do your resiliency analysis. And those fragility curves not only depends upon your, like what I told, that it will get shifted depending upon the state, like your affecting state, but also this has been affected by which component you are using, which material you have used, or whether there is a very old thing or a very new thing. So you can see this first image, that is depends upon your intensity on the fragile curve specific damage state. So if your intensity measure is, let's say, first at the IM1 and it has been increased, that means your wind speed has increased. So the failure probability of that equipment will obviously increase. So it has increased from P1 to P2. So that is one effect, or you can say one specific feature of your fragility curve. Now, let's say one pole has been multiple time affected by high wind. So obviously, let's say the first time it has not broken or it has very affected by a minor damage, but cumulative effect of this minor damage for let's say 2 years, 5 years, or 10 years time, that will become very huge, and that will make the system brittle. So if you see this image at the middle up, like top row middle one, if you see that this solid red line, that is like an, you can see the fragility curve for a particular equipment when it is a brand new. Okay, but multiple times it has been affected by a damage probability, and it has been, the damage accumulation has been happened, and after certain years this fragility curve can shift to the left. So for the same intensity level, the failure probability for the new one was quite low, but for the old one, like when it has become old or the accumulated damage has become very high, the failure probability also become very high. So it is not like that you did your fragility curve analysis at the beginning of your power system planning, and depending upon that you have planned your system, you like you placed your poles and the lines, and then you forget, and you think that okay, now my system is resilient. That is not the case. With time, with your minor effects, minor, even the minor effects can shift your fragility curve to the left side, and that will increase the failure probability. Now if you see the specific cases, that is for the distribution poles for the high wind speed, then you can see that obviously what I told, that if your pole is vertical pole, that means it is exactly 90-degree standing tall, and compared to a pole which is 30-degree leaning from that 90-degree level, that is at the 60-degree from your ground, the failure probability is different for the same wind speed. The 90-degree one has lower probability of failure, and your 30-degree leaning has 18.3% more probability of failure. Again, if you see the construction material, if you have a wood or you are using steel, depending upon that as well, your probability of failure or the fragility curve shifts. If you see the steel one, it is very strong, so obviously it can sustain, let's say 55 meter per second wind speed. So at 55 meter per second wind speed, if you have a steel pole, its failure probability is only 30%. But if it is an wood pole, then you can see the failure probability is 100%. So the material what you are using, that also changes the fragility curve. Similarly, if you see the aging effect on the probability fragility curve, if it is a new pole, if it this solid line, this is more prone, like lesser prone to failure. And if you go to 25 years, 50 years, or 75 years old poles, then the fragility curve shifts to the left side. So if your fragility curve shifts to the left side, then your failure probability is increasing. And if it is shifting to the right side, that means your failure probability is reducing. So as a power system engineer, when you do the resiliency analysis, because the natural scenario or the natural phenomena is always to shift the fragility curve to the left side. That is the natural phenomenon that we called as your depreciation, any material. Obviously, all the time with the rolling years, its fragility curve will shift at the left side. But as a power system engineer, when you do the resiliency analysis and when we are taught, telling about grid hardening algorithm, or we want to plan our system resilient for a cyclone or let's say an extreme weather event, we want this fragility curve to be shifted at the right side. So that is our main aim for the resiliency analysis. Then you have this distribution line. Obviously, those are more brittle compared to your pole. So if you see the comparison between the line and the tower or the pole, line is more brittle. That is the blue one. That has the higher probability of failure come at the low speed event. Now the span, length span, that means the span between two poles. If that you are increasing, that means the hanging distance of your distribution lines is also increasing. So that has a very high probability of failure when a wind will attack. But if the span is very short, so at that time your probability of failure is less. So all these considerations, like when you will plan whether you will go for a wooden pole or a steel pole, whether you will go for a 90-degree inclined pole or a 30-degree inclined pole, whether you will go for a new pole or you will just refurbish a 25 years old pole and then use it, whether you will keep your distribution line span 200 meters or 500 meters. All these considerations we take when we do the resiliency planning. Then we come to the impact quantification and we will see what are the impact of all these events on now this fragility curve, and we will see the failure probability of the actual scenario under the actual scenario, and then summarize the total expected damage for the entire network, number of failures, so that means how many equipment has got out of order, outage area, how much economic loss, and what are the restoration need we have to do. Then we'll do the network level analysis. That means some portion of the network is already de-energized. Can we run the rest of the network properly? If we want to run, then what extra effort we have to take. That means if it is an over voltage condition, then which reactive power absorbers or inductors we have to turn on, and which locations, or which generators needs to be slowed down, or the generation from which generators needs to be cut down. All this analysis we do at the network level. Then we do the visualization of the entire system and we do the report writing. So to do this analysis or to uh, measure this resiliency level, normally two different resiliency measures or measurements are done, that has been calculated and has been reported in the reports. That is, the first one is the expected outage duration. That means for an event, if it passes by, what is the duration? That may be what I told in the very beginning, at the very beginning, that it is taking 2 to 3 days time. So that is your duration time. And the area, the system wide expected energy not served. That means whether if you have a, let's say your energy capacity is 30 gigawatt and you have cut down almost 20 gigawatt, then your system wide expected energy not served will be very high. That measurement will be very high. So we always want your this expected outage duration to be as low as possible, and this not served one is also as low as possible. If these two things are low, that means your resilient, your network is a resilient network. And to do that, to minimize this effect, we take certain measures, or you can take certain steps to do this distribution system resiliency enhancement. And there comes this planning stage. We can do it at the planning stage and we are doing at the operation stage. What is actually your short-term resiliency and your long-term resiliency? So the long-term resiliency, this is actually includes your planning where you will do the vegetation management. That means you will take care that a branch of a tree will not fall down on your power lines. You will do the hardening methods. That means what I told, that you will use, let's say, concrete or steel poles. By replacing your wooden poles, you will use bundle conductors rather than a single stranded conductors. You will use component upgrading. That means you will replace all your old components with the new one, and you will place the backup facility. That means you will keep DGs, diesel generators, at the remote locations to supply when the main grid will go out of order. So those are all the planning phases work. And when actually the system will like response, that means actually the event will occur, though you have all these things with you, still you will see that certain amount of area will get disconnected. So at that time, what you will have to do? So whatever the backup supply you had, or the microgrids, or the solar power generation, or the electric vehicles, or the storages you have at your dark region, you just activate them and form a microgrid with those sources. Or maybe you move your mobile energy storages, that means electric vehicles, from the substation, your control centers, to the affected areas, and and just supply those critical loads. Apart from that, you can take the network reconfiguration. That means whether if you have a single line to supply your loads for a particular region, that is not a very feasible solution, because if that line get affected, so if a single point failure has happens, so entire downstream area will get disconnected. So if there is a provision that you have a normally open switch in your network, which will connect the area, this area remote end, with your substation, and whenever this kind of event occurs, so at that time only you will turn on that portion, and that is like a backup supply. So if that is possible, then that is also increase your resiliency. You take all these measures, you log them, or you collect those data, do the documentation, and those documentation is actually needed for the planning. So you can see these are like a closed loop thing. If you do a proper planning, if your system is actually modeled or actually planned considering the long-term resiliency, then your system operation or these operating scenarios can operate properly. Like your whatever the measures, like this microgrid formation. If you have planned for the backup supply, if you have planned for the DERs, then only you can do this microgrid formation. If you have this mobile energy storages, then only you can do this operation at that time, or the reconfiguration. If you have those things, then it can operate. And then we'll see whether this resiliency measures or resiliency metrics that has been improved or not. And that feedback we take while again planning for the next few years. So that is how the resiliency study keeps on doing each and every year, for specifically for those areas where these events are very frequent and has been affected. That is in our country, that is mainly your Bay of Bengal coastal area. If you go to Japan, they are mainly preparing themselves for earthquake resilient system. If you go to the South China Sea area, this Chinese government, they are building for against their typhoon, making their system resilient against typhoon. And obviously, US, the Texas, Florida, Georgia, those states, they are making their distribution grid more resilient or strong enough to withstand the frequent hurricanes they are experiencing. So there are few grid hardening options. That is, the first one is that you will upgrade the physical infrastructure. That is, other than having overhead lines, can we plan for underground cables? If you have an underground cable that is very strong and that is also not exposed to your high wind, so that will make your system stronger. Can we change the poles, wooden poles, and replace them with the steel or the concrete poles? We can design our system as a wind resistance design. That means shorter span between two poles. We make the lines harder. That means we use the bundle conductors. So that is from the infrastructure point of view. From the mechanical or the civil infrastructure point of view. As an electrical point of view, we can form small smart grid or the microgrid infrastructure at the local end. That means we will have the automatic switch and the reclosers, that if something bad happens, automatically those areas will get disconnected or become islanded. You have an advanced SCADA system or your PMU installed. That means any disturbance happens at any location of your network, and that has been instantly reported to your control center, that your control center can take the actions instantly. If that is possible, if that smart grid technologies are there, then obviously the prevention, or you can say the taking the corrective actions, will be easier. Because if your system get disconnected and at that instant your control center come to know about that event, then mobilizing those rescue teams, or you can say the rescue efforts, is very easier, or that will be very fast. The third thing, to create system redundancy. So all these solutions are quite costly, because creating the redundancy is also costly, because you are placing those things like that loop distribution circuit. That means we know that mostly the distribution networks are radial in nature, because that is a cost effective solution. If you want to create loop, that means you have to place more and more lines, switches, then your substation, your transformer, distribution transformers, everything. So that will enhance the cost. But if you keep that loop distribution circuit, that will provide an alternative path. Obviously, the microgrid backup supply, and the DERs. So all these solutions are quite costly, but if you compare the investment cost compared to your cost which we incur after the disaster, those are hugely different. Because if we install all these things, it will take, let's say, 1,000 crores. But when Amphan kind of cyclone attacks your Bay of Bengal area, and that is costing almost 9,000 crores. So almost 9 times economic loss you are experiencing if you are not prepared, if you are not making your system prepare for it. So this is a typical planning uh, topography, or you can say schematic of a power system, of a distribution system, where we'll take the planning decision, what I have told. You will take the wind profile, wind speed data, you will take the fragility curve data to model the event and the component. Then you do the Monte Carlo simulation to generate the scenarios. And you normally we generate almost 500 to 1,000 scenarios, and that will be implemented on the distribution network, and to see the overall loss. And we see how much loss we are incurring, economic loss or maybe your technical loss, all these things we will consider. And again, like whenever you have designed that loss value, we again generate scenarios from that loss as well. Because we want to be very, very specific while taking a planning decision. So we don't want even, let's say, a event which has a probability of occurrence 1%. If you are not prepared about that, and you have invested thousands of crores of money for building your system, and that 1% event has occurred, let's say after 5 years or 10 years time, your entire capital investment is going to scrap. So not to, we cannot afford this thing. So after doing this loss analysis, again we generate scenario from that loss analysis, and that has been used to do the resource decision, for potential planning of the resources, like which line you have to do the hardening, which poles you need to make it replaced, where you have to plan your DGs, where you have to plan your mobile energy storage, where you have to plan your static storages. All these resources decisions are taking. Obviously, that has been done by considering the planning cost, that is, the capital investment into consideration as a constraint, and how many areas you can fit it. Because you cannot put a diesel generator everywhere in the network, though that is a most resilient option or the solution, but you cannot do it. So let's say your budget only uh, allow you to place 5 to 6 DGs in your entire network. So how to optimally place, or how to find the optimal location of those DGs in the entire network, that the maximum amount of customers or maximum number of customers can be catered from those DGs. So that is the optimal planning frameworks. Those for the long term resiliency. Now, if we come to the short term resiliency, at that time you need to activate all your equipment or the backup supply or your backup measures what you have installed during the long term planning. So generally we do the pre-event analysis, and there we see that which are the areas which will get experience the fault or will experience the disruption, and at the post disaster event we'll see that we'll check where to mobilize our resources. That means if you have a repair crew, if you have a mobile energy storage, if you have your the DG power, so how you can activate or you can maximum utilization you can do, that the critical customers will obviously get the power after few hours, or your and other customers they are also getting connected one by one with less time. So that analysis is done for the short term resiliency enhancement. Few standards are mostly followed to design your system more resilient. That is, first one is the IEEE standard, that is 1366, that is guide the electric power distribution reliability indices, that will define the SAIDI, that means the outage duration index and outage frequency index, and measuring outage impacts and the resilience on the network. And then 1547 series, that will say the support from the DERs that you can get from at the islanding condition or the voltage right through condition. So those are the IEEE standards. Then we have that National Electricity Safety Codes, which will say that for your physical assets, that is your lines or your underground cables or overhead equipments, what are the design parameters of them, what are the construction element you have to use, how frequent you have to do the maintenance, and your how much wind and ice loading or the physical strength each and every equipment can withstand. So everything has been uh, standardized by this National Electricity Safety Code. And then American Society of Civil Engineers, which says that minimum design load for buildings and other structures, like if a particular pole or towers needs to be placed at some places, how much wind speed, snow or flood or any kind of other loads or hurricanes or storms it can withstand. And depending upon that, those manuals, actually the power system planners, they do design their system. So at the end, I will say that obviously there's power system resiliency analysis, which has not been explored much 20 years before, but now people are aggressively working on that because of this increasing threat from this climatic hazard. Because in our country also we are seeing this multiple times. This is starting, let's say, this starting from the May time to till October, we are experiencing multiple times the cyclones has been attacked. Even not only the cyclones or not only the high wind states, even if we see the flash flood, if we see the earthquake, this kind of natural hazards are quite common nowadays and affecting any country in this world. So this needs the technological advancement for the power grid, because any compare like similar to your civil infrastructure, like your homes, your buildings, if they get destroyed because of these events, as it take few years to rebuild all these structures, similar to that, if your power system structures get re- destroyed by those events, it also takes few years to completely revive from that situation. So there, if we can contribute or you can do for the technological advancement, and that can only be done by collaborating with the other stakeholders. That means your collaboration between your meteorological department, that they will give you the good prediction of each and every event. They will give you the data of past history of the cyclones, and then the policymakers with the power engineers. So with that, I will conclude my talk and thank you for patiently listening me. And if you have any question, I will be happy to answer.
Thank you very much, Dr. Subbu, for your excellent and insightful presentation. Definitely, your talk has provided us with great understanding and practical perspectives of grid resiliency and its impact and impact of natural hazards on the grid resiliency. So now I request participants if they have any question or if they want to discuss something with our expert. Anyone have any question or query? They can ask to our expert. Okay, thank you, Dr. Subhopal.
Okay.
I think nobody have uh,
Yeah.
any question at this moment, but later at any later stage they may ask you something, and you have also
Yeah,
shared
sure.
your email ID. So on behalf of all the participants and the organizing team, I extend our heartfelt gratitude to you for taking the time to be with us today and for sharing your knowledge and the expertise. We
Thank you.
truly
Yeah.
appreciate your contribution to success of this FDP. Thank you very much.
Thank you. Yeah. Thank you. Thank you very.
Thank you. So with this remark, today we are closing this session and hope to see you all in the session tomorrow. Thank you. Thank you to all the participants also.